gadget. Okay, so one of the last things I wanted to discuss on this course, which is coming up on your exam, it's only a short question, but it's actually a very important subject, right? We, so far, have been making little small C# programs, and at some stage you have to go out into the real world and make really big C# programs that solve real problems, right? And it's actually very important. You know, we've used lists, for example, we've used arrays. It's very important to choose the right data structure to solve certain types of problems, which only occur when you're dealing with large amounts of data. Alright, so I'm sure you're all heard of things like machine learning and data warehousing and data analytics and all of that sort of stuff, right? It's very important. And there are certain types of problems in there which are solved. They're actually solved, but they're very interesting problems in computer science. You don't need to know the detailed solutions, but you do need to know what's the right approach to use when solving these problems. So a classic one, actually here we go, we're on the net here, right? So we discovered earlier on there's 425 million Gmail addresses, right? If you go onto gmail.com and you try and create a new Gmail account, you type in your Gmail account and instantly it tells you whether that account is already taken, doesn't it? Can you think of another example of where something needs to be searched incredibly fast over huge amounts of data?
One word in Google.
Exactly. Well, that's one example. Certainly. Yeah. When you type in a word in Google and it searches through billions of web pages instantly and gives you search results. Another example would be DNS. Right. When you type a URL into a web browser, you know there's billions. There's billions of registered domain names, and instantly your browser sends off a request and it retrieves back the 32-digit IP address for the computer. So you might wonder, how in the hell are computers able to do that kind of searches very fast, right? Huh?
DNS takes it in parts.
Well, if you even in parts, right? If you were to type in something like news.com, okay, so that has a unique 32-bit number, and it's one of 4 billion possible combinations. So does it need to start at address number 0, go through, search through them all until you reach the very end to see if it's there? No. How does it work then?
DNS.
Hash table.
It uses a hash table. Okay, so have you guys done this with Richard Lawler, or with? Are you familiar with the concept of a hash table? Do you know the binary search algorithm on binary trees? Have you come across them? So these are ways of searching through large amounts of data very, very efficiently. And when you have a large number of things that need to be searched, for example, you want to search through all possible Gmail addresses, right? This is done using a hash table and hash lookups. And even in your own programs, even when you're writing an SQL database, I'll give you an example at the end where we can make an order of magnitude improvement in the speed of an SQL query by creating an index on a table, which is a hash lookup. All right, so how a hash table works, it's beyond the scope of this course. It's more of an algorithms thing, right? But in a nutshell, what happens is, for every entry in a table, a hash is created. What's a hash? It's just a numeric representation of it. So if you've got big long strings, for example, a unique number will be created which represents that string. And there are various different hashing algorithms which will create that unique number from a sequence of characters. And then those hashes are stored in something called a binary search tree, a binary tree, all right? Or it could even be just stored in sorted order, and then you can use a binary search algorithm to search. And those searches on hash tables and things are very, very fast. So if you come across big O notation, yep. So what you're aiming to get, like if you have 4 billion, right? If you have 4 billion entries, you know, if you take something which is ON efficient, then that means the speed of searching it is dependent on the number of entries in the table. Isn't that right? So for example, if you have 10 or 20 or 30 entries, this algorithm is, an ON algorithm is fine. If you have 4 billion, then that means you have to start at element number 0, go all the way through as far as 4 billion if you want to search for something. So an ON algorithm is not good. What you want to try and get is something which is either O1, which is the optimal. In other words, it doesn't matter how many entries are in there, it's always equally as fast to search. But more commonly what you get is an O log n search algorithm, right? And an O log n, does everybody know what log means? What does log mean?
Logarithm.
Huh?
Logarithm.
Logarithm. What does logarithm mean? Yeah, so it's to do with powers, right? It doesn't really matter actually what log n means, right? It doesn't actually matter, and it's just a maths thing to do with powers. But if you plot log of n, if you start at 0 and you put 0 into the log formula, and then you start putting sequential numbers into the log formula, and you plot the graph, you see that it looks like this. So in other words, at the very start, the efficiency of the algorithm increases quite a lot. But then once it reaches a certain size, you know, once we get to 100 or 200, in fact for a log it's very, very low. It doesn't get any more, the value doesn't get any bigger. It just stays, you know, it stays pretty much constant. And when you get an O log n efficiency algorithm, like a binary search, like a hashed lookup, that's really good, because it means that you can put 1 billion entries in. It might take a fraction of a second to look it up. You can put 100 billion entries in, and it's only going to still take a fraction of a second to retrieve it. So an O log n algorithm is what you want. Something that when you look at the efficiency of it, you see that the more entries you put into the thing, it doesn't get any slower. You know, an ON is that. In other words, like 10, 20, perfect, not too bad. But the more entries you put into the thing, the slower it gets, right? So we'll have a look at some algorithms in C#. And C# has got some really nice data structures. And by the way, this is a very common question in Google interviews. You know, it will be, how would you check to see if there's a unique Gmail address? Right? And the answer is that you use a hash table. You do hash lookups. So we'll write some C# programs and we'll check out the efficiency of some data structures in C#. So I'm just going to click New Project. I'm going to make a console application here. Call it console app 1. Can everyone see that okay? So I'll zoom in a bit, right? So first of all, it's very cool in C# because there's a class called a stopwatch class. And the stopwatch class allows you to measure the timing that it takes for certain things very efficiently, okay? So first of all, I'm going to create a new stopwatch here. Just so I can measure the efficiency of these things, right? New stopwatch. We'll fix that error here by right-clicking on this and resolve by going using system.diagnostics. So there's a couple of methods on the stopwatch. When you want to start the stopwatch, you call stopwatch, have a guess? Let's start. So that starts the stopwatch. Okay, and it starts measuring time. When you want to pause the stopwatch, you just call, or stop the stopwatch, you call stopwatch dot stop. Perfect. Stopwatch dot stop. Alright? And then you can restart the stopwatch and you can count the amount of time that has elapsed. So we'll start out with a plain old array in C# and we'll see how efficient an array is. Okay, so first thing we'll do, let's see, what did I do here? Let's create an array of 100,000 elements and we'll put 100,000 integers into the array. And we'll see how long that takes, right? So I'm just going to go int equals new, in fact let me just go int. The size of everything here is 100, not. Alright, so we've got 100,000, right? So equals new int 100, size, let's use size. So I'm just declaring an int of that size, okay? Int IA for int array equals new int. And let me populate that. In fact, let me do all of this inside the stopwatch thing and just see how long it takes to declare that integer. Put 100,000 elements into that integer array, okay? So let's go for int I equals 0, semicolon I is less than IA dot size. In fact, let's just use size. Semicolon I plus plus. And we'll just put the int I in, right? So I at position, IA at position I is equals to I. So we're just going to put the number in at the position in the array, just for the help, to see how long it takes, right? So then we call stopwatch.stop and we'll print out, you know, to see how much time has elapsed. So that's to declare that integer array, just populate it with a random, you know, with integers, right? So we can go console.writeLine, stopwatch.elapsed. So that's going to tell us how long it took to declare that array and to put in 100,000 entries. Now, just for comparison, we'll do the same thing with a list. All right, so what's a list in C#?
Collection.
It's a collection, right? So it's kind of like an array. What's the difference between a list and an array?
An array is immutable.
Array is, well, an array is mutable, yeah? Because, well, the array, I suppose it is immutable in the sense that once it's allocated, you throw it away to reallocate it. But you can change the elements in an array. Yeah, no problem. What's the difference between a list and an array?
Grow and shrink.
Yeah, an array, a list can grow and shrink. Yeah. So a list is kind of like a managed array. So you know, you might imagine if you were loading stuff up from a file, probably better to use a list because you don't know how big the file is, you don't know how many elements you're going to have in advance. So we'll use a list instead, right? Let's make a list of integers. So I'm going to call this li equals new int size. All right. So going to be a certain amount of discovery here, okay? And what we will do here, sorry, that's wrong. New list of integers, and then we call the constructor for it. Now we'll do the same thing with the stopwatch here. We can call stopwatch.restart, which actually sets the stopwatch back to 0 and then starts counting again. So we'll do the same thing here, and we will basically insert 100,000 entries into the list and see, is it slower or faster, right? So we'll go li.add, so that's how you add something, and it resizes if it needs to, and then we'll call stopwatch dot stop. So pretty much those lines of code, you know, they're kind of functionally equivalent, and then we'll print out how long it took to do the same thing with the list. All right. So yeah, we'll print out the elapsed time, and then we'll zoom out, Command Z, and we'll just compare the amount of time. So we're basically looking at comparing, just going through a list item by item, adding all the elements, and then the same thing with an array. So we'd be looking basically, which one do you think is going to be faster? The list or the array? How many people think the array is going to be faster? How many people think the list is going to be faster? I would think the array is probably going to be faster because the list may have to resize. I don't know, it depends on what the default amount of data is. I think the list is probably going to be slightly slower, but we're not going to notice a huge difference here. By the way, all of these differences are going to be sub-millisecond, right? But it's fine because the stopwatch will give you down to a fraction of a second. So if I hit F9 and hit F5 there, so we get the elapsed, close that window there so we have a bit more space, close that one. So we're going to get the elapsed time. All right. Oh, that's interesting. Yeah, look at that. So the array, 0.003965 of a second it took to populate 100,000 entries. The list was 10 times slower. You notice that? So it was 10 times slower to use a list than an array. And the reason for that is because the list is managing itself in the background. It may decide, okay, well, I'll allocate 200. Once I get more than 200, I have to go and reallocate. So it's doing that for you, but there's a trade-off. All this kind of stuff is the kind of thing that if you were working for Havoc, you would have to know this inside out. Not just for the C++, not for C#, but for C++. Yeah?
You can predefine the size of the list when you...
Let's try it.
When you allocate it.
Let's try doing that. If you do, what we'll do is I'll copy the same amount of code here, and I'll do this a third time, but this time I'll pre-allocate the list to say, give me 100,000 entries. Is it part of the constructor, is it?
Yeah.
List capacity. Oh, sorry, so I'll pass size in here. I think it's still going to be slightly slower, right? Okay, so I'm going to throw away the old list. I still think it's going to be slightly slower. Alright, so we have another look at it. Yeah, it actually hasn't made any difference. Oh, it has. Well, okay, so now this time, now this is just because every time you run your program, depending on what's going on in your computer, it's still 3 times slower to use a list than an array. So that's interesting, isn't it? So this doesn't make a huge amount of difference with 100,000, but imagine you had 1 billion of these, and imagine you were trying to run this algorithm hundreds of times a second. So you really have to think, you know, very optimally. Should I use an array? Should I use a list? List is more convenient, but an array is faster. Alright, let's do something now, right? Let's imagine I want to search that list to see, from start to finish, I want to see if there's an entry in there. We'll time how fast it takes to search the array, okay? Oh, hang on, before we do that, an array, if you want, one of the big disadvantages with an array is what? The big advantages of a list. Huh? It's fixed size, right? With a list, you can delete stuff from the end, you can delete stuff from the middle, you can delete stuff from the end or from the beginning. With a list, what is a list? Underneath What's its data structure?
The same as status.
It's an array. Underneath it is actually an array. So the consequences will say, you know, you can do an insertion at the start. What are the consequences of doing an insertion at the start of an array? Is it going to be faster to do an insertion at the start or at the end? It would be way faster to do it at the end. At the end is going to be O1 efficiency. At the start is going to be ON. Because it depends on how many entries are in there. Because if you think about it, if you insert something at the start, it's going to take everything and pull it down one. So with a list, right, we can actually test that. Okay, so let's take our list here. So our list is called LI. And let's restart the stopwatch here. And we will try doing two different types of insertions, right? Let's do li.insert. So I'm going to insert the value 0 at position 0. So I'm going to insert something right at the very start. Then I'll stop the stopwatch and print it out. Okay? And then I'm going to do the same thing, but I will basically, instead of calling insert, I'll just call add. Now you think about what needs to happen when you call that insert. It actually needs to take all the entries and move them down one. So this is going to take a lot longer to do an insert at the beginning. And in fact, what we can try is doing an insert halfway along for the hell of it. So the first when you do insert is the index. So let's take size divided by 2. So I expect that to be roughly half as long, because it's only got to do half the amount of movement, right? So then we do an insert, then we'll stop the stopwatch, we'll print it out, and then, so we stopped it, sorry, let's start again. Restart it should be, yeah. If you do start, I think it's like pausing it, you know. I think it will just keep on counting. So we need to do restart.
We need to take out the console line.
Sure. So, oh yeah, so there we go. So I do my insert, stop it, and then that, and I've restarted it. And I've inserted halfway along. So now what I want to do is add one right at the end, just to check the efficiency of it, right? So to add one right at the end is going to be very fast when I do add. So I'm just going to add an element to the end of it, right? So restart, stop. So hopefully, if our theory is correct, this one's going to be slow, this one's going to be about half as slow, this one's going to be instant, or ON efficiency. So let's run the program and see what happens. Yep. Okay, look at that. So that's slow. This one, is it half as slow? No, it's not. It's not nearly as slow, but it's certainly not as fast as this one. This one is almost, you know, this is 0.00004 of a second to add something to the end. But this one, 0.00025 of a second it costs to do an insertion right at the start. Can you see that? So it's an array underneath, right? And inserting things at the start much slower than inserting things right at the end. So the next thing, let's try and do a search, right? To do a search, there's no alternative. We've got to start at the beginning, go all the way through to the end. Because it's not, in this case it is sorted. And we could use a binary search, but we can't assume that it's sorted. So say we want to iterate through every single element in the array to do a search, right? We're going to do that. Let's see how long that's going to take. So I'll restart my stopwatch again. And then I want to go for int I equals, here's an interesting thing. Is a for loop the same efficiency as a for each? Doesn't make any difference. We'll try it out, right? For int I equals 0, semicolon, I is less than li dot, is it size or count? It's count, isn't it?
Yeah, it's count.
Okay. And now I just want to go something like to find, it doesn't really matter here, but I just want to make sure that this code gets equals 9, doesn't matter. Okay, and bool found equals false. Alright, so I'll just write a little for it. Okay, so if li at position I is equals to toFind, this is the only way. The only way to search an array is to go through it element by element, right? If we found it, then I'm going to set found to be equals to true. Now you can't just jump out when you found it, because you might find another one. Say you wanted to search for the last occurrence of it, you know? So you might want to have to go all the way through, or you might want multiple finds. So even if you find it, you still have to keep on going, right? Let's assume that. So we'll stop the stopwatch and we'll print out how long that's going to take. And it's going to take quite a while. So we'll print out that. And that's basically the only way to do a search. Alright, so that's just to make sure that it does the find. So we'll see how long it's going to take to do the search through every element in the array, in the list. So that's quite a while now. We're actually getting into the danger zone here because we've got 0.001 of a second. So that's 100th of a second it's taken to search through 100,000 entries there. So, you know, if you're to do that 100 times a second, it's going to take you 1 second. So it's certainly not efficient enough to search through all 4 billion Gmail addresses to see does one exist or not. Because we're only at 100,000 here and it's already taken 100th of a second. Can everyone see where we're going here? Alright, we're testing the efficiency of this algorithm. So, it turns out that there is a way to do this kind of hash table lookup. And it's built into almost every modern programming language. C# is no exception, right? And C# actually has 3 different classes for doing this kind of hashed lookup. These instant lookups, these O log n lookups. And the class in C#, does anybody know what it's called?
Dictionary.
It's called a dictionary, right? There's also a thing called a sorted list and a sorted dictionary, which do similar things. But I don't know what the difference between them all is. But a dictionary is an index lookup, right? So, first thing about a dictionary, so we just use lists and arrays, and now we're pretty clear about the difference in efficiency between both. Just for the hell of it, let's do a for each loop. I'll copy and paste all of this, and I'll just do a for each loop, just to see, is it as efficient, or too slower, or faster, or whatever. So let's go for each. Int val in li. That's what I call it, isn't it? Yeah, li. So then you can just do if val equals. So yeah, just before I do it, just have a look at that and tell me if that looks okay. That's basically a for each loop. So iterating through them element by element using a for each loop instead of a for loop. We'll just see do these take the same amount of time. For each loop is very slightly faster. About 10% faster. The for loop is about 10% faster than the for each loop. Sorry, wrong way around. The for each loop is about 10% faster. Now, I don't know if that's going to be consistent.
Try it again, yeah.
Yeah.
Does it depend on the implementation of the collection? Could be different for list or an array.
Could be.
That was slower again.
Yeah, it's still a little bit faster though. I don't know. It could depend on the data structure. It could depend on what you've held in it. It could be dependent on whether it's a list or an array. Do you think it's dependent on whether it's a list or an array?
I mean, linked list would be quicker to iterate through.
I don't think so.
I mean, if you do for each on a linked list, then you have to traverse through every element to find the nth element. And when you do for each, you could just jump from one to another.
Yeah. Say again. I'm not sure I quite got that. I don't think it makes too much difference if you're iterating through them element by element. The difference between a linked list and something like an array would be that a linked list, you can do an insertion anywhere in the linked list and it's equally as efficient. However, if you want to do a sequential search from start to finish, they're both pretty much the same.
If you try the for loop on a linked list,
yeah,
and you access an element by its
I see
ID.
what you mean, by its index. In other words, by doing random access. Yeah. So a linked list can't do random access. You know that, don't you? You've done linked lists, have you? So you know with a linked list, you can't say jump to the 20th element. Because you have to start at the 0th element, then find the next, until you reach element number 20. This is a bit more explicit in C++ because in the standard template library in C++, you've got a linked list class and something that implements an array. But in C# you only have this list class, which is an array. There is no linked list class as far as I know. Maybe there is. Anyway, we can see that searching from start to finish is not very efficient. So now I want to show you how to use a dictionary, right? So a dictionary is another one of these generic types. And this is really kind of useful because the dictionary maps keys to values. And it does it by means of a hash table and an index lookup. So the thing about it is you can specify what the keys and values are. Right? I'll do a very straightforward one and then we'll do the efficiency one. So for example, if I wanted to map names to ages, that would be a classic use of a dictionary. So you can map a string, and the first parameter in here in the little angle bracket thing is the key type, and the second parameter is the value type. So you can go dictionary mapping strings to integers, and you can call that ages equals new dictionary, and this is going to map strings to ints, and there we go. So to put something into it, you use kind of array type notation. So you go, for example, ages, and we'll get a few ages. What's your age and your name there?
Richard.
Richard, yeah, that's right. So we'll map a string, Richard. And what's your age, Richard?
33.
33. Shocking old. Huh? But not as old as me. Just so you don't feel bad, I'll put my one in here, right? I'm only slagging Richard. Happy days when I was 33, huh? They're a distant, long distant memory for me. Sure, it's all ahead of you. What? What's that?
Still younger than I.
Okay, we're going to throw you in there. What's your name and age?
Patrick, 44.
Holy God. That's very old. I'm only slagging.
It's alright.
And then just for a bit of contrast, let's throw in Jason, because Jason, you're about what, 14?
12.
What age?
8.5. My ball rolled across the ball.
Go on, give me an approximate integer age. 8.5?
23.
23, okay. That's still oldish. Is there anyone younger than 23? I'm sure there's loads of people younger than 23.
Obvious.
Darren, what age are you then?
19.
Oh my God!
Got lost in the way of the shops.
19, is it? Okay. So anyway, we're mapping names to ages. And then, as you might imagine, you can get stuff out here. Console.writeLine. I'm sorry for anyone I offended in the last bit of the lecture there. You can get stuff out by just going ages, Darren. Like this. So you access the elements in this thing as if it was like just an array kind of notation. You see that? The interesting thing here is when you go ages Darren, it's doing a hash table lookup here. So while there might be 1, 2, 3, 4, 5 elements here in this one here, if there was 5 million elements, it would take only a tiny little bit longer to do the lookup. Because you can do key value searches here, right? And it's using a hash table. On the other hand, a dictionary uses a lot more memory than a list because it has to create the hash table in RAM. Okay, so that's the hash lookup. So let's just test the efficiency of this, right? I'm going to do another dictionary, and you can see how this is the normal way that you use a dictionary, right? But I'm going to make a really hacky dictionary, just to show you we can test the efficiency. I'm just going to map ints to ints, and I'm just going to put the same value as the key as the value, so you can see, how we can just test the efficiency of this, right? So I'm going to call this DT for dictionary test. New dictionary, int, comma, int. Alright. And now, let's do the same test again. Let's start the stopwatch. We'll put 100,000 entries into that dictionary and see how long it takes compared to an array, okay? So, there's my stopwatch restart. Zero, semicolon, I is less than size. Alright, I'm just going to DT at element number I. So this is kind of hacky, right? I'm just mapping ints to ints, just for a test. Normally you would map some sort of key to some sort of object or a reference or something. I'm just going to DI equals I. So I'm just going to create 100,000 entries in the hash table. And then I will stop this. Stopwatch dot stop, and then we'll just print out how long that took. Now I'm just going to put a note in here. This is the dictionary, just so we can see the dictionary compared to the array. Now what we should see is that the dictionary takes a lot longer to set up, right? So D is that one, and then up here let's do the list by comparison. This was the list when we're adding stuff to the list, and then this is going to be L colon. Alright, so what we're looking to see is that the dictionary, ideally, I presume it's going to happen, let's try it out and see. Now to add 100,000 entries into the dictionary should take a good bit longer than to add 100,000 entries into the array, because it's got to create the hash table. Alright, let's have a look. So there's the list. Yeah, look at that. 008148 to do the list. However, it's at least 10 times slower to set up a hash table, a dictionary type, with the same number of entries in it, right? But watch this. This is the cool thing about dictionaries and these hash tables. Look how quickly you can search that, right? I called it DT, add element number. There we go. That's it. I've now searched for element number 100,000. Now this is almost, this isn't quite log n, this isn't quite O1, but it's O log n. So it's very, very fast to go searching through that entire dictionary and search for that one particular element out of it. Now, what I wanted to just be clear about here is, okay, I'm using integers here, so it looks like an array, but this could be a string, or this could be actually an object. You know, more likely this is going to be an object that I'm using for a key, or a string is quite common. You know, you might have a key that you're using as a string, but just for this example here, to set it up really quickly, I'm just going to use integers, right? So now I've searched for element number 10,000 in there, and it's almost. I'll tell you what. Let's actually see how efficient it is. I'm going to restart the stopwatch, stop it, and then I'm going to print out the value. Alright, so in other words, this is doing a search. Alternatively, you can just do di. I'm sure there's some way to check for a key. Key exists, contains key. There we go, let's try that. And then my keys are all integers. So there's one, that one. Alright. Oh, sorry, it should be. That's a method. So there we go. So that's essentially doing the same thing as my for loop up above. So just to be clear about what we're comparing with what, let's print this out here. This was the search, the list search. That was my list search. And then my hash table lookup. Okay, so let me just zoom in there, make sure that's right. So restarting, searching the list to see does it contain that, stopping, and then printing out the elapsed time. Alright, so using that dictionary, hopefully we're going to find that it's a lot faster than doing the array search. Alright, let's have a look up here. So the list search, yeah, 001, so roughly 1/100th of a second to do the list search, and you can see there that it's about 100 times faster. Or is it 10 times? It's about 10 times faster to do the indexed search. Alright, so that's the advantage of that hash table thing. Of course it takes longer to set up, yeah? But it's way, way faster for searching. The interesting thing about this is this number is not going to go down, it's not going to go up. If I was to change that number, it's not going to, actually let's run it again. Because this is an O log n efficiency algorithm. So that's 00011. If I add an extra 100,000 elements, I wouldn't expect that number to change substantially, right? So it was 0001, wasn't it? So now I'm going to add twice as many elements in there and see how long it takes to search. It's the same. You see that? So it doesn't matter how many elements I add to that dictionary, it's always going to be roughly the same to search through because it's doing this kind of indexed lookup. So this is how Gmail is able to allow you to type a Gmail address in and instantly give you the answer, yes, it's there or it's not. Does everybody follow that? So when you're designing these kind of big systems, and if you're asked this kind of question in Google, you use a hash table, you use an indexed lookup. And these are available in almost every programming language. PHP, all array types are hash table lookups. They're hash table lookups rather than being indexed lookups like an array or a list. So there's one last thing I wanted to show you, just to show you like how this applies, you know, in a real world, like a genuine real world sort of computer system, and how you can make use of this kind of knowledge straight away, right? So I'm sure you've done some stuff with SQL, haven't you? So this is again an application of using this technology, right? Using this kind of index lookups. So I happen to have a database here called, does everybody understand what does anyone want to ask any questions so far, just before I show you this last bit, because we're running out of time. Did you get the general idea? So you use the right data structure depending on how you need to access the data. A linked list is great if you want to start at the beginning and go all the way through until the end, but it's very poor for doing random access. An array is very fast for doing random access, but it's very poor if you need to insert things in the middle or at the beginning, or delete something from the middle at the beginning. A hash table is slower to build, but it's much faster for searching. Okay, so that's kind of the general guidelines. Anyway, I have a table here called Tune Index. So this is from TunePal, okay? And this table has got 22,000 entries in it. And so there's all kinds of queries running against this database every minute. You know, there's hundreds of queries getting run against this. And this needs to be mega fast, right? So somebody does a search on their mobile phone for a tune, it needs to come back within 10 seconds, absolute max. And it also needs to be able to handle hundreds of concurrent queries, loads of people searching for tunes at the same time. So here's the actual tune table, right? And there's a key. If you look here, I've actually taken this, and this is have you used this thing before? Who's used this? This is PHP MyAdmin. All right, so this is just a web-based interface for a MySQL database, right? So it allows you to administrate your database through a web browser. It's nothing fancy, right? It's not really part of this course, but I'm just showing it to you. But if you look down here, you see that there's only one index, which is the primary key index, right? So if we go over here to browse this data, and I take the first tune here, this tune here, and I'm going to write an SQL statement. Select star from tune index, where TunePal ID is equals to, single quotes, paste that guy in, single quotes, and we'll see how long this query takes to execute. So I'm going to actually copy that query as well. Control C, click on go. Alright, so it took 0.0151 of a second. Alright, so it's pretty fast. But it will still have had to have gone through every single one of the 22,000 tunes to see how many matches there are. You follow? So watch what we'll do here, right? 0.0151 of a second. If I come back here and I choose show more actions to add an index. There we go. So to add that index took 0.2 of a second. And now what it has done is it's gone through every one of those TunePal IDs and it's created one of those binary search trees for them. So now when I write this SQL query, watch how long it takes. Hopefully it's going to be shorter. Okay, let me delete all this stuff. Yeah, that's the same, that's the right query. Look how fast it was by comparison. So it's useful to know that that is one click, right? And I've been able to speed that up by a factor of about 1,000. You know, so that's by creating an index. So whenever, actually an interesting thing, whenever you are doing databases, right, and you know you're going to have more than likely thousands and thousands of rows in each table, anytime you're doing a join between two tables, create an index on the columns because it makes it hundreds, thousands of times faster. There's other types of indices you can create. For example, you can create a full text index, which does the same thing, but it actually extracts all of the words that's in, for example, you know, if you had a memo field or something like that, or a text field, it'll extract all the words, and it will generate one of those binary search trees for all of the words. All right. So that's data structures and efficiency and a real world application. All right. So create indices on any column that you need to do a lookup on, and you will notice that your database performs thousands of times faster.
Can you switch that indexing on?
Yeah. I can just go and delete that index, right?
Yeah.
So if I just go back in here, take that index again, there's my TunePal ID, and I drop the index. Now it's going to go back, instead of using that index, instead of using that dictionary lookup, it now has to go back to doing the lookup that it did previously, which is basically searching through each one. Go away. This is... delete. So now it's going back to doing the search the way it originally did. It's really slow again. Alright. Cool. Alright, that's it.